The topic of this presentation is understanding JESD204B in less than 30 minutes. So it definitely won't be a complete guide to JESD204B, but I will try to cover like the basics, the most important subjects. And if you're still interested into it, there are some like links at the end of the slide that you can follow if you want to further dive into it. My name is Lars-Peter Clausen. I work for Analog Devices. And so first introduction, what is JESD204B? And it has been designed and it supports up to 32 lanes per link, and each lane can transport up to 12.5 gigabits per second of raw data. The actual useful payload is a little bit less because a little bit of protocol overhead, but overall you can get like 40 gigabits per second, 400 gigabits per second over one link, which is quite a bit. And the standard, the JESD204B or JESD204 standard, not only describes how to get bits from A to B, but it also assigns meaning to the bits. It describes how, how to map a sample onto those high-speed lanes. This is all defined in the standard itself. Unlike, for example, if you are using a converter that's using parallel LVDS, there's no common standard how to map the data onto the LVDS lines. And other things that the JESD204 standard offers is multi-chip synchronization. So if you have multiple chips, multiple ADCs, multiple DACs, and want to capture synchronized data or transmit synchronized data, the standard defines how to do this. So it is no longer chip specific. And the other very important thing is deterministic latency. We will talk about this in more detail in a moment. But it basically allows you to make assumptions about how much time will elapse between when the conversion was done and when the data arrives at your logic processing device. Quick timeline. So JESD204B or JESD204 went through 3 revisions. There was the first one in 2006, and it only had one lane, and it was only running at 3.125 gigabits per second, and people quickly figured out this is not enough. So in 2008 there was the first revision, JESD204A, and they added support for multiple lanes. But it became pretty apparent that it's still not enough. So there was the second revision or third revision, JESD204B, which raised the limit for each lane up to 12.5 gigabits per second. And if you kind of follow this timeline, right about now should be time for the next standard. And there are actually devices shipping that go beyond what the standard has to offer and run at 15 gigabits per second per lane. And I think there will also be a REF-C at some point in the future soon. And the other important thing that JESD204B introduced was the deterministic latency. There are 3 different subclasses, so subclass 0 doesn't offer deterministic latency, and 1 and 2 basically have different methods for achieving deterministic latency. And it also introduced a more flexible clocking scheme. In the previous iterations, you had to supply the same clock at the same frequency to all the devices in the system. And with JESD204B, it's possible to run some of the clocks at harmonic or subharmonic frequencies. This means you can, the clock going to your converter might be twice as fast or 4 times as fast as the clock going to your FPGA. Because let's say you have a converter running at 1 giga sample per second. You won't be able to run the logic in your FPGA at 1 gigahertz. So you maybe want to scale down, run it at 250 megahertz, and this was introduced by the standard. So motivation, why do we actually need this? Especially for the software-defined radio stuff. Why do we care about JSD204B? And what we're seeing is that the increasing data demands, like a lot of the new mobile communication standards have rather wide channels. Wi-Fi, the latest version, AC, has channels which can be up to 160 megahertz wide. LTE supports channel bundling or channel aggregation up to 5 to 20 megahertz channels and to one logical 100 megahertz channel. And at the higher bands, like what's in discussion for 5G and also Wi-Fi AD, you got channels which are more than a gigahertz wide. Like for example, for Wi-Fi AD, I believe it's like 2.6 gigahertz your channel. So you have to kind of like capture all this data and get it somewhere. And another trend we're seeing is the adoption of diversity transmitters and receivers. In the most simplistic way, this is kind of like MIMO, where you're just using it to gain diversity gain, which means you have multiple antennas which are placed in a certain specific pattern, so you can receive the same signal multiple times. And if one of the signals gets some kind of distortion, you set things up so that the other one doesn't, so you then can still recover your signal that you're sending. But more and more wireless standards are actually designing support for diversity into the standard itself, like with Wi-Fi AC. There's kind of like provisions for measuring the channel and actually using the different multipath propagations of your signal as separate channels. And for this, of course, you need diversity transmitters and receivers. And for each transmitter and receiver you add to your system, you're going to double your data rate or increase your data rate. And the last trend that's becoming very important at the moment is direct RF, which means you are no longer having your analog mixers where you're down modulating your signal of interest, but you're capturing the whole spectrum up to your signal of interest, like you capture 2 gigahertz, 4 gigahertz, maybe even more, like 10 gigahertz at the same time, and then do digital processing on it to extract your signal of interest. And for certain applications, that is like gets you better results than doing this in the analog part of your design. But why does it mean that we actually need something like JSD204B? Why can't we just keep on and continue what we had before? And to like parallel buses. And the issue with parallel buses is there are two ways to increase your data throughput. Either increase the number of pins or increase the clock rate. If you increase the number of pins, you can send twice as much data. If you double the clock rate, you can send twice as much data. More pins has the issue of routing. So if you like have 40 pins or even 60 pins, it gets really complicated routing this all, and you really have to kind of like hope that your receiver device has the same mapping as your transmitting device. Otherwise, you have to kind of like you need a lot of layers to be able to route it. And the other issue, the more lanes you have, is the more power you use. So power becomes also an issue at some point. And the other thing is, if you increase the clock rate, you are running into the issue that for parallel bus, you need to capture all your data at the same time, right? You have your clock, and then you have your data. And both the clock has jitter, the data has jitter, there's skew between the clock and the data, and all of these kind of like depend on different operating parameters. They will change with the process, with the voltage, with the temperature. And voltage here doesn't mean kind of like, at 1.8 and 3.3 you will get different propagation delays. It actually means that your power supply, which has a uncertainty of like plus minus 10%, even though it's set up for the same nominal voltage, will introduce different skews and delays here. And the higher up you go with your clock frequency, the smaller this window will get, and eventually simply becomes impossible to match it. So, and this is where JESD204B or JESD204 comes into play, and a quick overview of how such a system looks like. You basically have 4 components. There's the clock chip, and the clock chip is connected to some kind of reference clock. And then the clock chip will typically contain a PLL and a couple of clock dividers. And the clock chip is responsible for generating all the clocks that are used inside your system. And it's also responsible for creating the so-called sysref signal, which is used for synchronization between multiple devices. And then up here you have your transmitter. And on the other side you have your receiver, and in between there's a high-speed serial link. And as we discussed already, there can be up to 32 lanes. And there's one additional signal, the so-called sync signal, synchronization signal. And to establish a link, what the receiver does in the beginning, it pulls the sync signal down, and then the transmitter will send some kind of synchronization sequence. And once synchronization has been completed, the receiver has locked onto the signal that's being sent here. It will deassert the sync signal, and the transmitter will start sending the data. But in addition to this, the sync signal can also be used once the link has been established to do error reporting. So if something goes wrong, if the data is no longer good, if there are lots of errors, the receiver can assert the sync signal for one clock cycle to tell the receiver at the transmitter that something's wrong and maybe it's time for a reinitialization of the link. Right, and there are 2 different classes of transmitters and receivers. There's the so-called converter devices and the logic devices. And the converter devices are your ADCs, DACs, and so on, and the logic device is the processing. And in addition to this, as I said, JESD not only defines the physical link layer, but it also does a lot of other stuff. And the standard defines 4 different layers. There's first of all the application layer, where all the application-specific processing happens. And since this is application-specific, there's obviously nothing in the standard that says what needs to be done here. But what the standard defines is the interface between the application layer and the underlying layer, which is the transport layer. And what the transport layer does, it's responsible for the so-called sample framing and also lane mapping. This means it takes the raw sample data and packs it in a certain way that everybody agrees on, all JESD204B devices agree on, and then distributes this data onto the different lanes. And then the next layer is the link layer, and the link layer is per lane. So from the transport layer will pass so-called octets, which is 8 bytes of data, or 8 bits of data, to the link layer, and the link layer will do some processing, like scramble the data. It will do the so-called character replacement, which we'll talk about in a moment, and it will also do 8B, 10B encoding. And then at the physical layer, we have really the high-speed serial interface, and this typically involves the conversion from parallel data into serial data. And on the receiving side, you also do clock recovery, and often you also include signal shaping, because at 12.5 gigabits per second, your transmission line is really transmission line. It's no longer normal data. So you need to do some signal shaping. And yeah, so let's talk about the converter device. The converter device, there are 2 different kinds. There's the ADC device and the DAC device. And so first of all, a converter device can contain multiple converters. And typically in modern converter devices, in addition to just the data conversion, there's some kind of processing. And here is basically the split where the JESD layer starts. First of all, we got the framer, which works over all data and then distributes the data onto each lane. And typically, you also have a PLL in there to generate the clock for the high-speed serial link. And on the receiver side, on the DAC side, It's basically the same. You have one lane, or you have your lane-specific processing, then it goes into the deframer, and the deframer distributes it to all the converters, to all the DACs. And what's important is that all those ADCs and DACs inside one device are all running synchronous. And logic device looks basically the same, except that instead of having your converters here, you have huge block of custom processing. And the one special thing about the logic device is that one logic device can actually interface to multiple converter devices. The so-called multi-point link, for example, you need 4 ADCs, but your converter device only has 2 ADCs. So you can take 2 of those and combine them into one logical converter device which has 4 ADCs. Then the link. So as I already said, the link consists of multiple independent lanes, and on the physical level, you use this differential current mode logic. It's kind of like LVDS, but a little bit more power to be able to handle the high speeds. And it has an embedded clock rather than a separate clock. This way, you no longer have to deal with this clock and data matching. And as I said, it does the data scrambling. And the data scrambling is optional, but it's highly recommended because if you turn off data scrambling, you your data might contain certain patterns, and this will result in certain spurs, which will then show up in your actual data. So that's why the data scrambling should pretty much always be enabled. And also the CDR expects data scrambling to be enabled. And a link or a lane has a couple of parameters. There are lots of them, even more than what's shown on the slide. I don't want to go into detail of all of them, but you can see there's lots of things which can be configured, which tell the sender and the receiver how the data is sent over the link. Let's talk about deterministic latency quickly. So propagating data over a link takes time. Like you might have pipeline delay, and also propagating the signal from A to B over your transmission line takes time. And this time, so part of this is fixed. You know how many pipeline cycles you have, but part of this is also variable and depends on manufacturing differences and environmental conditions, again, process voltage, temperature. And there are certain systems and algorithms that are very latency sensitive. For example, closed loop control system, where you transmit something, then measure it, and then adopt your transmit based on this, like DPD. And also radar, where you want to measure the runtime difference between 2 signals, is very dependent on latency. So ideally, you always want to have the same latency. And the way JESD does this, it does not remove the latency from the system, but it compensates for it. And the way this works, there's the so-called local multi-frame clock, which is kind of like a slower version of the frame clock. It's kind of like a local clock, slow clock generated inside the device. And all events that are deal with synchronizing things are synchronized to this local multi-frame clock. And how it works is, first the receiver asserts the sync pin, deasserts the sync pin, which means it's ready to receive data. Then on the next clock, the TX starts sending data. And it will take a little bit of time until the data reaches the receiver. And there's also a certain amount of variance in how long it takes. And the way JESD makes sure that your latency is always the same, it uses kind of like a FIFO, and it delays the data until the release opportunity. So it doesn't matter whether the data arrives here or here. The first sample that will be released to the application layer will be at this release opportunity. And for this to work, of course, your variance needs to be less than one local multi-frame clock. And let's quickly talk about data integrity. So 8B, 10B allows some detection of a few simple errors, but not so many. And what the standard defines is, if an error is detected, it should actually be replaced with the data of the previous frame. But what many implementations do is they just assert some kind of error signal, error flag, because from a processing point of view, it's better to know that you got an error rather than replacing your data with random data. But there's no additional data protection, like no CRC or forward error correction on the link itself. And if you look at what kind of data JESD is actually transporting, so it's not very kind of high fidelity. You have your DAC, which will do digital to analog conversion, which is a noisy process. On the receiver side, you have an ADC, which does analog to digital conversion, which is a noisy process. There's always background noise, which kind of affects your data. And then, of course, you all know the RF channel, and the RF channel is kind of the worst thing. You have lots of interference that will flip bits, destroy bits, whatever. And so what the JESD link has to offer, or needs to offer, is just it needs to be better than all of this. The bit flips that are introduced at this level need to be the noise floor of this part, because the upper layers will already know how to deal with certain kinds of errors. We'll skip this. So software support. Since JESD is kind of like a standard, you might expect there's really great software infrastructure based on top of this, but the current situation is not so great. There's no common infrastructure, and typically the system integrator, the guy who puts together the converters and puts them onto this PCB and maybe writes some software, needs to research all the constraints of all the different system components. Different converters, different logic devices have different constraints for these parameters that I showed before. And so you have to go into these data sheets and figure out how does all of this work, and find a configuration that works for all of them. And then you have to look up the magic register values that map to those settings and program them. And typically the application developer, the software-defined radio person, has to work with what's provided from the system integrator, because changing this is it's a big hassle. And we're trying to change this with the development of the lib JESD204. And the way it works, it has a built-in database of all the converter devices, logic devices, and so on. And all the constraints that are imposed by those devices. And those rules, or this database is not kind of like a database with A, B, like this supports 1 lane, 2 lanes, and so on, but it's rather a database of programmatic rules where you specify relationships. And then the system integrator only needs to specify, in addition to the constraints that are already found in this database, constraints of his board. Like, for example, a converter might support 8 lanes, but only 4 lanes are wired up on a certain system. And then the application developer can dynamically change the configuration at runtime. For example, change the sample rate. And I think this ties in with the talk we've seen before, because people want to get stuff done. They don't want to care about all this low-level stuff. They want to build a software-defined radio applications. And hopefully what this libJESD204 will provide will be able to achieve this. And the other part the lib will do, it will automatically map a configuration to register settings. And that's it. Questions? Or yeah.
Are there any open cores for interfacing with this on FPGA?
Yeah, so there's the MLabs, open source implementation of the JESD204B core. It's written in MyGen. Yeah, it's kind of like a special language. It's like Python, maybe a little bit like MyHDL, but different. And they provide an open source core, and let's see. This one will also be available soon. It's something we've been working on. It's the complete transmit and receive cores implemented in the FPGA vendor independent way, and it will It's not quite ready yet, but it will in the next 2 weeks appear on our GitHub repository. So yeah, that's the thing. One question over here.
Have you tested the MLabs core with your chips?
The what core?
You just mentioned an MLabs core. I wasn't familiar with
Oh, no.
Have you tested it with your chips?
I know that they're using our chips, yes.
Can you repeat the question?
Okay, so the question is, has the MLab core been tested with the ADI converters? And yes, it has been. They are using the ADI converters.
Is it an open source core?
This one is open source, yeah.
Cool.
Yeah.
You mentioned that when the receiver deasserts the sync line, the transmitter sends some synchronization information.
Mm-hmm.
You also send information about what the configuration parameters are of the sample and such. Is that contained in that configuration, or do you need to, on the receiving side and the transmitting side, both manually specify this is what I'm sending,
Yeah.
and the other side has to?
Yeah, so there's a so-called initial lane alignment sequence, and in this lane alignment sequence, you send the full configuration parameters over the link. But typically, you also program them on both sides. But if you had hardware which supported this, you could do it this way. So typically, there's a second channel for configuration using SPI or I2C. One question over here?
Clock from the set that you use to run the device.
Sorry, could you repeat?
And the recovered clock from the deserializer we use to run the device. In case, for example, of a DAC, they don't have to write the clock itself.
Yes, it could be, but the standard explicitly forbids this. Sorry, the question is, can you use the recovered clock to run the device itself rather than distributing a separate clock to the device? Yes, you can, but then you don't get the deterministic latency, because your recovered clock will have kind of like random phase, depending, because you recover the high rate clock, and then you create a down divided clock for the parallel section of your processing, and the parallel clock will have random phase to your transmit parallel clock.
Won't be random itself, it will jitter.
No, we can talk about this later. I think that's one more question.
If you have a short one.
I think there was one over there.
So, is the fixed latency mode mandatory in the standard, or is there also an option for best effort mode or something like that?
So the question is if the latency is mandatory in the standard, and the answer is no. I mentioned this quickly in the beginning. There's 3 different subclasses. There's subclass 0, and subclass 0 basically just says instead of having this release opportunity, just release the data when the last lane arrives. Okay, that's it. Thank you very much.